Good. Okay, so here we want to continue in this LAN switching lessons, and we're moving on to STP. What exactly is STP? STP is a spanning tree protocol, and you can see that I've already connected another cable to these two switches. Before now, the switch 1 is using port 10 to connect to switch 2. But I've gone ahead to add port 11 as well, so the two switches are connecting to each other using at least 2 cables. The idea here is that if one of the cable goes down and there is a need for someone on switch 1 to reach out to someone on switch 2, communication can still continue compared to when it's just one cable and that cable goes bad. The switches will no longer be able to access each other, and if there is a need for someone on switch 1 at that time to reach out to someone on switch 2, then communication will fail because the cable that link the switch 1 and 2 together is bad. Okay, so what are we trying to achieve here? We are trying to have redundancy in network connection. So redundancy meaning that we have 2 connections, and in a situation where one of the connections go down, we'll still be able to communicate as if nothing has happened. So we are using yet another cable like this to connect this guy on port 11. So that's actually what I have done. So we are connecting this guy like this. So this is on F0/11 and also on F0/11 this side. Okay, so you can agree with me that redundancy is good. Yeah, redundancy is good because if one of these cables should go bad, the other cable should be like a backup that would allow the both devices on different switches to reach out to each other if there is a need for them to talk to each other. Okay, so in as much as redundancy is good, I see a problem here. What problem do you see here on this topology? We already have one cable connecting the switch 1 to switch 2. Adding another cable, I've explained that it gives us a redundancy. So if one cable goes bad, there will be no problem. But in as much as we have redundancy, what other problem do you think we have here? So we are trying to create a solution where we no longer have a single point of failure, and now another problem has come up. I see a problem of loop. Did you see that? So what exactly is loop? Loop is repetition of signal. So when a signal is repeated on a network, it results to what we call loop. So what do we mean by repetition of signal? Now the switch 1 is now connecting to switch 2 with 2 cables. Let's assume that we have allowed sales department to be able to communicate to finance. So if that is the case, that sales can talk to finance, then it means that if a PC here is forwarding data packets to a PC here, what do you see here? Most likely this PC here is going to receive that packet twice, because whatever data that the PC here on sales is trying to forward to that PC on finance is going to be passing through the first cable, and it will also be made to pass through the second cable. So you get the idea. So for the same data to be repeated on both of these cables is what we call loop. Right? So are we going to now say that because we don't want to have loop, we're going to do away with one of the cables? No, because we still need redundancy on the network. We want to be highly available, so we want our network to always be available, and a failure of one cable shouldn't lead to a network or reachability issues when it comes to the users connected to both switches. Okay, so we want to keep the second cable because we need redundancy. But what we do not need here is loop. Why? Because if we have a loop on the network, everything will be slow. So that's the impact of hardware loop, which is loop created as a result of physical connection between two or more networking equipment. So how can we have a redundant connection and yet we will not have signals repeated, which will cause loop? Well, it's very, very possible. So how? Let's go to the whiteboard. So there is something we can use to achieve that, and that is called spanning tree protocol, or STP. So what spanning tree protocol does is that it helps us to have a loop-free switch network. So just like I've explained in that diagram earlier, if we have two switches that connect to each other, so this is switch 1 and this is switch 2, and it's not really a good idea to use one cable to connect the two switches, because if this cable should go down, this switch can no longer reach this switch, and so use at least two cables. Why we are using two cables is because we want to be redundant. We want to ensure that the network communication between the two switches is not brought to a halt just because the cable connecting the switches is bad. So have a backup cable, so to say, where the first cable goes down, the backup cable is being used by the two switches. And that's what spanning tree helps us to do. So how can we turn on spanning tree? Well, we don't need to turn on spanning tree because it's embedded in all switches, but then we have flavors of spanning tree. As you can see on the whiteboard, we have the common spanning tree, which is the IEEE spanning tree. This is IEEE 802.1W. Actually, it's 1D, right? So IEEE 802.1D. By the way, IEEE is the Institute of Electrical and Electronics Engineer. So the common spanning tree, it takes this type of spanning tree 50 seconds to detect a link failure and then transition to the backup link. So how does spanning tree work? So if we're using two cables to connect these two switches together, spanning tree is going to ensure that one of these cables is not allowed to send traffic, right? So that we do not have loop. Okay, so spanning tree is going to look at these two switches and decide to shut down one of the links and allow only one link to be used at a time, right? And if one link that is being used, maybe the cable gets bad, spanning tree is going to detect it in how long? In 50 seconds. And it's going to now remove the blocking that is placed on the second link so that the second link comes up and the two switches will still be able to reach each other now using the second link, since the primary link is no longer available. Alright, so the spanning tree that takes up to 50 seconds to detect that one link is down, let me transition to using the other link, is called common spanning tree, or the IEEE 802.1D spanning tree. Now, what exactly will the spanning tree use to know which of the links to block? Well, there is this thing they call root bridge election, right? So the root bridge election is what the spanning tree is going to use. So it means that the moment we connect this switch to this switch with at least two cables, the switches will hold an election. Yes, you heard me right. There will be an election between the switches to elect the root bridge. Root bridge is what I call master switch. So there should be a need to have a master on the network, right? And then one of the switches will now become a slave, so to say. And the slave will, of course, have to be reporting to the master. So what are the criteria for making a switch a master, which is also referred to as root bridge? Well, two criteria. One is switch priority, right? And the second criteria will be switch MAC address. Now, good enough, all switches by default have assigned priority. So if these two switches are brand new switches, then it means that priority cannot be used as a tiebreaker to elect one of them as a master. Okay, so if they are all brand new switches, then their priorities will be the same at 32,768. This is assigned priority by default. It comes with the switches from factory. Okay, so if priority is actually preferred to use as a tiebreaker, but in a situation where priority of the two switches are the same, the MAC address will be used. So if the priority of the two switches are the same, it means that the switches probably are both new, or the default settings have not been tampered with. Okay, so in a case where the priorities of the switches are not the same, then the switch with the lowest priority will win the election. Okay, so once the priority of this switch is maybe anything lesser than 32,000, and this one is 32,000, then the switch with a lower priority will be elected as the master switch on the network. And in a situation where the two switches have the same priority, they will no longer use priority to elect the master, but they will look at each other's MAC address, and once again lower is better. So the switch with the lowest MAC address on the network will be elected as master switch or the root bridge. And so once that election is concluded, then the switch that is not elected will be shutting down one of its ports, right? Okay, so as we have these two cables connecting these two switches together, the switch that is master, both of its ports will be green. That means that both of the two ports will be forwarding packets, while the other switch that is the slave, so to say, is going to shut down one of its ports. And let's not get into the details of which of the ports is going to shut down, but just keep it in mind that one of its ports will be shut down. In fact, it will never turn to green, so it will be showing amber. That's actually spanning tree. And the moment the cable that is being used goes bad, 50 seconds down the line, the other cable that is shut down or blocked is going to come up. Then another flavor of spanning tree is rapid. So basically, rapid spanning tree or RSTP is the IEEE 802.1s. So what am I saying? 802.1W. So this is 802.1W standard of spanning tree. And what actually that guy does is speed, right? You notice that the common spanning tree takes it 50 seconds to transition to the backup link in a case where the primary link is bad or is down. So if this cable here is down or is bad, it will take the common spanning tree 50 seconds to detect it and then move over to the other cable that was initially blocked. And so that block will be lifted so that the cable will become come up alive and traffic will be passing through that backup. But if you're using rapid spanning tree as well as multi spanning tree MSTP, the recovery time is just 5 seconds. So it takes the spanning tree 5 seconds to detect a link failure and then transition to using the backup link. Just 5 seconds. So that's like a whopping 45 seconds difference between the multi spanning tree, rapid spanning tree, and common spanning tree. Okay, so multi spanning tree is actually used in a specific environment where you want to group a couple of VLANs under one instance of spanning tree. Okay, so that's just a brief description of what spanning tree protocol is. So it allows two switches to connect to each other with at least up to maximum of 8 cables, and there will still be no loop because all other links that are not being used will be blocked and traffic will not be allowed to pass through those links, and one link will be preferred to be available, and once that link that is available is down, other links will be coming up one after the other. Okay, so we just want to ensure high availability. That's what spanning tree protocol is helping us to achieve without having a loop, which is repetition of signals on the network. I hope you get the idea of what spanning tree protocol is. We're going to stop this video here, and then when we come back, we'll jump into the topology and see how we can fine-tune spanning tree and how we can actually change the root bridge election. Note that spanning tree is already running by default, so there's nothing like let's enable it. It's already turned on by default. So what we can do in the next video is to fine-tune it and make it work better. Thank you so very much for watching, and see you in the next video.